In this video, we will discuss the derivation of the steady-state energy conservation equations. A little overview. So, in this video, we start with a steady-state case in a one-dimensional coordinate system, and then we expand the one-dimensional case to a two-dimensional case. Afterwards, we will expand the two-dimensional case to a case with heat sources involved. The next video will then tackle the transient two-dimensional problem and an extension to a three-dimensional problem. The learning goals of this video are first to set up energy balance for different types of cases. And from these energy balances, we then want to develop a differential equation using Taylor series expansion. We will also discuss what Taylor series expansion means. Then we will look into the required boundary conditions for the problem, and we will solve the differential equation for simple cases. So first, let's review what we have learned in the video before. We have looked into the steady-state case here, for instance, the conduction through the bottom of the pot, and we have seen that both temperatures are constant in time, and as such also the heat flow is constant in time. You see here on the right side the ingoing heat flow is equal to the outgoing heat flow. Then we have looked into the example of a coffee cup where due to the transient process and the addition of milk there is a difference, and there it's easier to maintain the high temperature of the coffee if we pour milk in first. And then we have also looked into a problem with heat sources. A very simple one is, for instance, a smartphone, where due to the ohmic resistances inside the smartphone, heat is generated and this heat needs to be removed. So, what have we learned regarding Fujis Law in the first lecture? So we see here a very simple example of a one-dimensional object, and there is a heat flux imposed on the right side. This heat needs to go through the body, and as such a temperature profile or temperature distribution inside the body establishes, and in this case here it's a linear profile because the heat that we put in on the left side needs to leave the body on the right side as well. This is described by Fujis Law. We see that this minus the surface times the thermal conductivity and the temperature gradient. Now for this specific example here, we can put in temperature 2 and temperature 1 and the thickness of the object dx. Now if we look at the steady state case without heat sources, we've already seen that if it's steady, the temperatures do not change, and as such the ingoing outflow needs to be exactly as the outgoing heat flux. How do we put this into a balance? Here on the right side it's already shown, and I would like to encourage you to put in the ingoing and outgoing heat fluxes that cross the boundaries of this control volume on the right side of the equation. So on the left side we have nothing, we have 0, and on the other side we have a positive one, it's ingoing heat flux, and a negative one, it's the outgoing heat flux. Now the outgoing heat flux we need somehow to describe, and we use for this the so-called Taylor series expansion. So we just say that the outgoing heat flux is equal to the ingoing heat flux plus a change of the ingoing heat flux over the coordinate x. So it's a partial differential of this quantity times this infinitesimal element dx. What is Taylor series expansion? So let's first look on this graph. We have here the heat flux depending on the local coordinate x. The black curve shows the actual course of the heat flux. Now it is assumed that this heat flux is doing a gradual change. We can know this heat flux here at the location x equal to 0, and we want to approximate the heat flux at the location x out. How can we do that? We can in the first part assume that the function value of the heat flux at this location x0 is together with the local gradient, so it's the first derivative of x0 times the distance here dx, so x minus x0 can be used to approximate the function f of x, so the heat flux at the location qx out. You see that this works not that well here because the slope here is changing, there is a changing gradient, and as such we are not 100% able to approximate this function value. So in order to approximate it on a higher order or better, we can also account for higher order differentials like f2 dash, so the second derivative of the function, also multiplied by the distance, but here the distance square, and also the denominator here is increasing, so the effect of those higher order differentials becomes less and less. How can we approximate this function in a really good way? First of all, we could reduce the distance dx. That allows to approximate this function much better. We see that this is on a numerical side interesting. If we increase this distance, or if we want to have a larger distance to approximate a function very well, we can use higher order differentials or a polynomial of higher order. For us, for the derivation of the energy equation, it is totally sufficient to assume that dx is very small, and as such we can approximate the outgoing heat flux by the ingoing heat flux plus the change of the ingoing heat flux times this infinitesimal element dx. Now let's go back to the energy balance around the infinitesimal element delta x. Our balance looked like this. We have 0 on the left side and the ingoing and outgoing heat fluxes that balance out each other. Now we can use Taylor series expansion to approximate the heat flux qx out by the ingoing heat flux qx in plus the local change of the ingoing heat flux times this infinitesimal element delta x. If we insert this in the equation above, we get an equation that looks like the following, and you directly immediately see that the qx in minus qx in will cancel out, and another term that cancels out because it's stated to be equal to 0 is the dx. We cannot cancel out the partial differential, otherwise we cannot continue our derivation. So removing these terms here will lead to an equation that the first derivative of the heat flux is equal to 0. So there is no change of the heat flux over this element size, which we assumed in first place already, because we said that if the temperature here in this element needs to stay constant and the thermal energy needs to stay constant, then the ingoing energy needs to be equal to the outgoing energy. And this is nothing else than the idea that there's no change of the heat flux over this element size. So we can apply Fujis Law. Q is equal to the minus lambda times A times the first derivative of the temperature with respect to x, and enter this into the equation. And because we have here the derivative and then import a second derivative here, we end up with an equation that is equal to 0 is equal to lambda times A times the second derivative of the temperature with respect to the coordinate x. How can we solve this differential equation of second order? So because it's a differential equation of second order, we do need two boundary conditions to obtain a solution for the temperature profile. What boundary conditions can we use? Let's look at our example here. We have the temperature on the left side, T1, and we have the temperature on the right side T2. And in between we have the length L. Our coordinate system starts here at x equal to 0 is the location where the temperature T1 is prescribed. So we can use for boundary conditions, for instance, at the location x equal to 0, the temperature is equal to T1. And we can use the second part that at the location x equal to L, the temperature is equal to T2. If we want to insert these two temperature information in the equation here, we need to do two integrations to obtain the temperature profile. So integrating this equation here twice, we will end up with the following equation. So the temperature is equal to the temperature T1 plus T2 minus T1 divided by L times the location X. And for the heat flux, if we are interested in the amount of heat that flows due to this temperature profile, this linear temperature profile, because from the second derivative, which is equal to 0, the first integration results in a constant, and the second integration results in a linear profile. So we can calculate our heat flux Qx, again applying Fujis Law, inserting now the temperature difference dt dx, our information about the temperature profile, and we end up that the heat flow Qx is equal to minus lambda times A times the difference T2 minus T1 divided by L. I think this is something which you might already have known, but it's just a simple way how to develop this temperature profile on a mathematical basis. Now we want to add this to a two-dimensional case. How do we do that? We have to account in our energy balance not only for the fluxes in x direction, but also for the fluxes in y direction. In this balance, we apply the same rules. So on the left side, we say, okay, there's 0, there's no change inside the control volume, and all of the fluxes that are across the boundaries of our control volume will enter on the right side. So we have here Qx in minus Qx out, that's in the red part the x direction, plus the heat flux in y direction going in minus the heat flux in y direction going out. And we see what needs to happen here is that there's a balance. The difference in the heat fluxes in x direction needs to be exactly the same as the difference of the heat fluxes in y direction. Otherwise, the amount of heat in our control volume will change, and because then if the thermal energy changes, the temperature changes, and this violates our steady state approximation. So how do we describe the Qx in? That we can do with the area here of the surface, so of the control volume. So this area is described by dy times the unit of 1, because we assume now a two-dimensional problem. And for the fluxes in y direction, it's very similar. We have this area here, which is described by the size of the element dx times the length of the element 1. Again, for the outgoing heat flux Qx out and Qy out, we need to assume Taylor series expansion. We again use the first order polynomial to describe this. It's exactly the same as we did already for the one-dimensional case. And now we can insert those parts in this equation. We know that from the one-dimensional case, this direct value Qx in will cancel out with the other Qx in. The only remaining term is the Qx in derivative with respect to x times dx. In the green part for the y direction, the only remaining part will be the derivative of the heat flux with respect to y times dy. And we see here, because we have a dy here on this side and an additional dx on that side, those can cancel out with the dx and dy that are already in this equation. So we end up again with an equation that has removed all those dx, dy values, and also the 1 can be removed. That's very important. Just make sure that these values cancel out in the derivation process. Otherwise, there will be something wrong. So if we insert that, we get again this equation which states that the change of the heat flux in x direction is plus the change of the heat flux in y direction together is 0. This will give us, with Fujis Law, if we exchange this qx again with the lambda times the first derivative of the temperature, we end up with a second derivative of temperature in x direction, and on the other side with the second derivative in y direction. And this leads us to Laplace equation, where 0 is equal to the thermal conductivity times the two temperature derivatives of second order with respect to the two different locations. Now let's finish this video with a steady state two-dimensional heat conduction problem with sources. So the energy abundance in this case looks very similar to what we have seen before. We have the fluxes over the elements or over the surfaces, so the ingoing and outgoing heat flux in x direction, the ingoing outgoing heat flux in a y direction. But in addition now we have a volumetric heat source Q dot 3 dash. So this volumetric heat source needs to be multiplied by the volume of the cell to be of the same unit. So we have here the unit watt to get to from the volumetric heat source to a unit of what we have to multiply it with the volume. So how is the volume described here of this unit cell? This is of course the size dx times dy times the unit 1. And we immediately see that the last term here also contains the two values of the infinitesimal element sizes dx, dy, which cancelled out here after applying the Taylor series expansion. So with Taylor series expansion and Fujis law, we end up with a Poisson equation, which states now that the change of the heat flux in x direction plus the change of the heat flux in y direction, expressed by the second derivatives of the temperature with respect to the two different directions, plus the volumetric heat source is equal to 0. And the volumetric heat source term, again from the unit, it's watt per cubic meter. This term can be positive, then we have a heat source, or it can be negative, then we have a heat sink. Now let's finalize the video with some comprehension questions. First, what is the steady state temperature profile for a homogeneous one-dimensional flat wall without heat sources? We have done this derivation in a first place. So we have seen that the equation that describes this problem is the second derivative of the temperature times the thermal conductivity times the area is equal to 0. Because it's a flat wall, the area is constant. Because it's homogeneous, the thermal conductivity is constant. We could easily skip those values, and then we see that the second derivative of the temperature is 0. So first integration will lead to a heat flux, and then after first integration we see that the temperature gradient is equal to a constant. Again, integrating it a second time, so we integrate this constant, we get to the solution that the temperature profile is of linear type, and we have to determine these two integration constants to get the temperature profile. Under which conditions does a Poisson equation become Laplace equation for heat conduction? we have seen that the Poisson equation includes the derivative of the temperature, the second derivative in the different coordinate directions here in x and y direction, plus in addition the heat source term. However, the Laplace equation does not include the source term for the heat, only the second derivatives, and as such we see that the condition that the Poisson equation becomes the Laplace equation is that the volumetric heat source term is equal to 0. Thank you for your attention.